The main construction of this talk will be the construction of convolutions, and we will use convolutions to work with cohomologies. But let's start introducing the most simple form of convolution that we will have, that is the concept of correspondences that was introduced by Fulton in his book of intersection theory. If you're not familiar with the concept of Chow groups or Chow rings, you may think of that of those Chow groups as cohomology elements, as a kind of black box that you can push forward Chow classes. You can pull back Chow classes under nice circumstances, and they have some nice compatibilities, like the projection formula and things like that. The Fulton's construction of correspondences was that a correspondence from a smooth case scheme X to a smooth case scheme Y is an element in the Chow group of X times Y. And the main construction, the nice thing about those correspondences is that there is a composition from A, X times Y, tensor product A, Y times Z, to A, X times Z, which is given by, let's say, alpha, beta, tensor product, this is send to, the projection towards X times Z, push forward, the projection, the pullback from X times Y of alpha intersected with the projection, the pullback of beta from Y times Z, where those projections are defined in the product of all X, Y, and Z. This is a well-defined map if all X, Y, and Z are smooth proper case schemes. And the nice thing about this composition is that, as any composition that you call something composition, is that it's associative. So if we have A, X times Y, tensor A, Y times Z, tensor A, Z times W, we have a map from this tensor product to A, X times W. No matter how we compose first these two elements and then with the other one, or first these two elements and then the other one, this composition will be the same thing. The idea that I want to generalize is that in these cases, we have some kind of information in X and W that we want to keep, and we have some transitory information of Y and Z that we want to forget. And these elements are relating information that we want to keep and information that we want to forget. We may think of the first composition as being some information about X that we want to keep, some information about some Y that we want to forget, and some information about some Z that we want to keep. And we want to associate to this graph this composition of correspondences. And to this other composition of correspondences, sure?
Should these be surfaces or
first, the construction of compositions and convolutions will be for smooth, proper case schemes. They work in a more general sense, but we will stay in this context of smooth, proper schemes. The next section of how we apply this to Hilbert schemes, and then we will be talking about smooth surfaces, because Hilbert schemes of surfaces are smooth and not in general. This composition here will be associated to some X, Y, Z, W, in the sense that edges will be representing transitory information that we want to forget, and vertices will be representing information that we want to keep. So the main construction of convolutions will be something like this. If we have a graph B, E, and some delta that tells me when an edge is adjacent to some vertex, and some labeling of xv, b in b, xw, y e, e in e. We want to expand this notion of composition to a notion of convolutions. And the idea is that for every vertex b, we will define some domain zb equal to xb times the product of all y-e's to the delta of v comma e. In this sense of graphs, this will be x times y and y times z, x times y, y times z, z times w, because here we don't have any labels, so we are assuming a spec of k. Those are the inputs that we will have in our construction, and our output will be the product of all vertex labels, b in b. Yeah.
E raised to the delta of?
B comma E, where E is going over all edges. So we are picking a fixed vertex, and we are multiplying the vertex label and all edge labels that are adjacent to the vertex itself.
Delta VE is 1 if
It's 1 if they are adjacent.
E goes to B.
Yeah, and it's 2 if it's a loop, and it's 0 if they are not adjacent. This can be in general defined whenever we have a map from b times e towards the positive integer, such that every edge is adjacent to some vertex, but it's pretty much the same. So we will be mostly focusing on graphs so far. And the constructions that we will use will relate to graphs. So the construction will be, and let's call some u, the product of all xb's, and the product of all y-e's. We have maps pi v from u, and this u will be analogous to this x times y times z that we are taking pullbacks to and then push forwards from u to the zb's. And we also have a projection from u to z. So our construction will be given some alphas, alpha v in the Chow group of zb. We will associate to those to the tensor product of all alpha v's. The push forward via pi push forward of the intersection of all pullbacks of alpha v's, b in b. The nice property of this construction is that in the same way as here, in the context of two compositions, it didn't matter whether we take this composition or this composition first. In order to compute a convolution, we can go by steps. We can pick a subgraph of our graph that defines the convolution, define the convolution in that subgraph, take the convolution of only those elements of those vertices, and then take the convolution of that vertex that results in the remaining alphas. The main idea in order to prove that is that for Chow groups and other cohomologies too, under nice circumstances, if we have a fiber square x, y, x prime, y prime, y prime, a fiber square such that the dimension of this map is the same as the dimension of this map, then taking push forward via this map and then pull back via this map is the same as taking pull back via this map and then taking push forward via this map. This is the main compatibility that we need between push forwards and pullbacks in our cohomology in order to define this convolution, and that convolution to satisfy the nice property that we can perform it in steps. Okay, that's the main idea of how convolutions work and how we will be working with convolutions, is that if we have that as a graph that we know how to compute a given convolution of a subgraph. We will compute that convolution in that subgraph and then compute the convolution with the remaining vertices. Now let's make some application over Hilbert schemes. In order to define maps using convolutions, there is we will need to define kind of canonical maps in products of Hilbert schemes, as we will be doing now. We will be using this notation here that if X is a smooth, proper surface, we will denote XD is the Hilbert scheme. Of the points of X. So this is the Hilbert scheme that parameterizes subschemes of X of dimension 0 and length D. Then a nice property when X is a smooth surface is that XD is also a smooth surface. So if we have some smooth scheme, it's natural to get interested in the intersection theory in that scheme. So we will be trying to study the Chow groups A, X, D. Previous works have studied, instead of the Chow groups of A, X, D, in the context of complex manifolds, Nakajima studied the cohomologies, the singular cohomologies of the Hilbert scheme. So we will be kind of emulating part of that work, but the methodologies that we are doing now will allow us to stay only in this cohomology and not need any auxiliary cohomology as some topological cohomology that Nakajima used in his work. Okay, let's define four non-negative integers. D0, D1, up to, let's start with D1, D1, D2, up to dt. Let's define U, D1, D2, dt as the subscheme of the closure of this locus in the product of X, D1, X, D2, X, dt, and X, D1 plus dt. We'll be taking the closure of these pairs, subscheme 1, subscheme 2, up to subscheme T, and the union of those subschemes equal to 1 up to T, where the subschemes I have disjoint support. And the dimension of this subscheme is 2 times D1 plus dt, which is half the dimension of this ambient space here. The nice thing about half the dimension is that convolutions add up how shifted the dimension of a cycle is with respect to half the dimension of the ambient space. We can use these schemes to define a product in the direct sum of A xd from D0 up to infinity. We will define the product of alpha 1 alpha 2. If alpha 1 has degree D1 and alpha 2 has degree D2, to be the convolution given by this graph here. X D1, X D2, X D1 plus D2. In order to define a convolution, we need to pick elements in the choke groups of all those vertices, the domains of all those vertices. For this vertex, we need an element in the choke group of xd1, so we are picking alpha 1. For this vertex, similarly, alpha 2. And for this vertex, we need an element in the choke group of xd1 times xd2 times xd1 plus d2. And here we will pick this standard element here. Whenever we are having some standard element, we will be encircling this vertex in order not to mess the diagram up. Is there? Okay.
I understand. So this, in the two corners, you're putting the point.
Yep.
Okay.
Uh-huh.
As the label of the vertex.
Yep.
Or not labeling points.
Yeah, not label points. I'm using some kind of.
Z, what you're calling ZV for that vertex is just XD1.
Yes.
And Z of the last one is XD2.
D2. And this one is the product.
So you have a class in cohomology for one Hilbert scheme, a class in cohomology of the other Hilbert scheme. You pull this back to the product of everything.
Intersect
With that U.
and push forward too. And this convolution lives in xd1 plus d2. So this product adds up the degree of the degrees. Similarly, we will be defining some other alpha 1 here. This scheme will allow us to define two operations. Similarly, here we added two things. Here we will subtract two things. xd, x d1, alpha 1, x d minus d1. This is if d is at least d1. Otherwise, we will define this to be 0. Okay.
Sorry,
Sure.
I think you said that, let's be clear. So in the first diagram, when you put the little dots around,
Yeah.
the second one is the dots.
Yeah. I forgot.
The label on that vertex is this.
The union of d minus d1 and d1. Because d minus d1 plus d1 is d.
I think it means that, so when he puts that circle, it means
Yeah.
he's choosing a class in cohomology which corresponds to that U.
Which is something standard. In this case, the standard elements will be these things here. In several proofs that I do, there are several standard classes, so I prefer to just encircle them instead of putting labels on each vertex for that class. Is everything okay? Okay. We will be defining another nice class and explain more or less how I will be proving theorems using this notion of convolutions. Given a non-negative d and a positive m, we will define this as the closure of this locus that is inside xd times x md will be the locus of p, p prime, where p prime, p is reduced, so it's a discrete set of points, and p prime, sure, p prime is supported in P with multiplicities. at each point. Be prepared. So the idea is that I have a set of points and a scheme supported at those points with multiplicity m at each of those points. The notion where these classes come from is that in Nakajima's work, the operators that he defined, they took unions and kind of took some kind of subtractions with points, with schemes supported at a given point, and these two classes are emulating those operations in the context of convolutions. Well, using this, this also has a dimension m plus 1 d, which is in half of the dimension of this ambient space of 2d plus 2md.
Sorry. So both of these products, so the first one goes from grade D1.
Yeah, xd1, tensor xd1 to xd1, d1 plus d2.
And the other one as well?
xd and xd1 to xd minus d1, because
So
the only vertex.
Really
Minus.
As minus.
Uh-huh.
Okay. Sorry.
So they are kind of, the first one kind of construct things and the other one kind of annihilate things. That will be the idea of how those operators work in future works where I define a vertex algebra structure, but we will not talk about that part now. Okay. We will be defining m dot alpha to be this convolution here. We'll be picking alpha in xd, and xd has a standard convolutor with xmd. So this convolution makes sense. I'm picking alpha in xd and something in xd times xmd. And this convolution lives in A of xmd, which is the product of all vertex labels. So this map multiplies the degree of alpha by m. In the future, we will prove that this is actually an action from the positive integers over h, but it takes a little bit of work to prove that. Okay. In order to use those convolutions and that nice property of that convolutions can be done in steps with these classes here, we need to know how those classes behave with respect to convolutions. So we will have some technical lemmas that we will be using. For instance, let's say that xd1, xd2, this has a standard class with x d1 plus d2, x d3, and this has a nice standard class with x d1 plus d2 plus d3. This convolution lives in a standard one here. This convolution lives in xd1 times xd2 times xd3 times xd1 plus d2 plus d3. So it is kind of
I can't read the indices.
oh, xd1.
I think you need to really write this much larger.
Okay. xd1 times xd2. This has a nice xd1 plus d2. Standard here, x d3 times x d1 plus d2 plus d3. Is it okay now? Okay. This convolution lives in xd1 times xd2 times xd3 times xd1 plus d2 plus d3. So it is natural to compare this convolution with just the standard element in xd1, x d2, x d3 times x d1 plus d2 plus d3. the result, a technical lemma tells me that those two are equal. The idea of how this technical lemma is proven is that we compute where the support of this convolution lives, and this convolution, the support of this convolution will be the same as the support of this convolution, other than some points that don't have enough dimension to generate any Chow class of the appropriate dimension. And on those points, the intersection that defines things is transversal, so this will be an equality. But we will not be bothering on, sure?
So it's not true that you can compare these things, like if you go up to a larger space? I mean, none of these things are pushed forward from something that you pulled back?
Yeah, I mean, yeah, that's how I compare these things. I compare the support of the intersection of those pullbacks, that push forward. However, since these classes are closures of things, comparing the supports is a little bit complicated. So there are some points that I'm not really sure if they belong to that support or not.
Oh, so even on the top level, they might actually be different. And this is something that happens only when you push forward that they become.
Yeah, I mean, this doesn't have anything that it's above that, because this just lives in this space. This convolution has something that lives above, and then I compare its image with this class here. And when I compare those things, I see that the points that are in one place and not in the other don't have enough dimension to generate any Chow class. So, and on those points, I see that the intersection that defines this thing is transversal, so there is no multiplicity that I have to consider here. Mm-hmm.
So how do you view each side? As an operator?
What do you mean? Yeah. This thing, when this property here will induce me two theorems with regard to those operations using this associativity of convolutions. For instance, a consequence of this equality here is that let me rewrite this convolution here. This is the nice thing about this language. Well, first. I mean, those are elements in the Chow groups. I mean,
whenever he writes a graph and he fills the vertices with these symbols, it means that he's taken a convolution already. So this
is an element.
Side is very nice to see. So you're taking this product of all these schemes that he's on this vertex, right? So let's grab the first vertex.
xd1 plus xd2 plus xd1 plus d2.
xd1 times xd2 times xd1 plus d2. And that circle in that vertex means that in that product of all of these things, he put that u there. So now in the other vertex, you have something similar with a different u that lives on xd2, xd1 plus d2 times d3 plus times xd1 plus d2. You have another u. So now you put those two u's on a huge product of everything.
The product of
that is
this
there.
plus this times this times this.
Right. So you
I
put them
pull
there,
back, I intersect, and
you
then
just
push forward to
intersect them and push forward. So now it's a class in the Chow group of the base.
of this product here, because this is the product of all vertex labels. A proper one, why we need how we use this equality of convolutions is that, for instance, let's rewrite this thing here, x d2 x d1 plus d2 x d3 times x d1 plus d2 plus d3, standard 1, standard here. This will be the standard class at x d1, x d3, d2, x d3, x d1 plus d2 plus d3. Okay, how we will be using these equalities of convolution is that, well, we know that this convolution is equal to this thing here. So this convolution here, we pick a factor. Here we transform this into an edge, x d1, and we pick alpha 1 here, where alpha 1 is an element in the Chow group of x d1. It's the same as if we had done the same here. We pick x d1 here, x d1 here, and we alpha 1 here. Why? Because we could have picked this convolution here and this convolution. I mean, this convolution is the same as first applying this convolution, and then the remaining thing with this part here. So this convolution here is this part here. We can do the same for this x d2 here, x d2 alpha 2, x d2 alpha 2. We don't care about this thing. And the same for x d3. X d3. X d3 in the edge. Alpha 3. Here the same. This is the vertex label. This is x d3. Here we pick alpha 3. This convolution is going to be the same as this convolution. However, we can do this convolution in other steps. We can first pick this part here. This part here, by definition, will be alpha 1, alpha 2, because it's alpha 1, x d1, alpha 2, x d2, and x d1 plus d2. So this is the same as alpha 1, alpha 2 in x d1 plus d2, x d3, alpha 3, and the label x d1 plus d2 plus d3. But this thing here, by definition, it's alpha 1, alpha 2, alpha 3. And this thing is pretty symmetric, so it doesn't matter if we took alpha 1, alpha 2, alpha 3, or alpha 1, alpha 2, alpha 3. So we now prove that this product is associative by this property here. So properties about how those standard elements relate via convolutions will give me properties about the operators that we have defined there. Another property that can be proven using this same statement here is that instead of picking an alpha 3 from here, we have picked an alpha in x d1 plus d2 plus d3. We will have gotten another property that tells me that alpha bar pairing alpha 1, alpha 2. This is the same as first taking alpha, alpha 1, and then that alpha 2. So annihilating some alpha 1, alpha 2 is the same as first annihilating alpha 1 and then annihilating alpha 2. So it's kind of an action of alpha 1, of the second argument and the first one. Other properties of convolutions will give me other properties of those operators. For instance, we can also prove that x d1 times x d2, x d1 plus d2, and then x m d1 plus d2. We can pick standard elements here. This makes sense, this makes sense, this convolution makes sense. This is equal to this other convolution here, x d1. First, I take the multiple thing, x m d1, x m d2, x d2. And the proof of this equality of convolution is similar. I look at the support of where this convolution lives. I see that the difference between those supports doesn't have enough dimension to generate any extra elements in any extra Chow class, and see that the intersections that I care about are transversal. So those two things are equal. This also makes here x m d1 plus d2. This also makes sense. This is d1 times md1, d2 times md2. This is md1 plus md2 is equal to md1 plus d2, so this also makes sense. They live in the same place, x d1 times x d2 times mx m d1 plus d2. A consequence of this equality here is that if we pick an alpha 1 from here and alpha 2 from here, this will give me m acting on alpha 1, alpha 2. Alpha 1, alpha 2. On the other side, we will get m acting on alpha 1, m acting on alpha 2, and the product of them all. This is going to be equal to m acting on alpha 1, product m acting on alpha 2. So this m action is distributive over products. How much time do we have? Okay. The idea of my work is that I use these operators to define analogous operators to the ones defined by Nakajima. The Nakajima operator for every gamma in AX, I define an operator and m positive integer. I define an operator Nakajima m of gamma. Let's use this notation better. Gamma m acting on alpha. Well, this will be defined in H to H. This will pick alpha, and this will take it to alpha, destroying m acting on gamma. And gamma minus m, and the same way H to H will take alpha, and it will take it to alpha product m acting on gamma. These operators are analogous to the ones that Nakajima gave in his work. And the commutator of those operators are quite nice. For instance, if both m's are positive, those operators will commute because they are taking destructions by something. And taking destructions by something will be both compositions will be destructions via the product. So Nakajima gamma 1 m1 composed with Nakajima gamma 2 m2. This will be the same applied on alpha. This will be just alpha destroying m1 acting on gamma 1, m2 acting on gamma 2. And this is, so they will commute. Similarly, if both m's are negative, they will also commute. It is a little bit more complicated to compute the commutator when one index is positive and the other is negative, but we get a nice formula that the commutator of Nakajima gamma 1, I always forget this part, -1 to the n -1, yeah. Nakajima gamma 1 m1 and Nakajima gamma 2 m2, and this is going to be equal to m1 times delta m1 plus m2 0, the pairing of gamma 1 and gamma 2, and the identity operator.
Oh, sorry, perhaps I didn't read. So the second n is n gamma minus m? So no, in the
Where?
Yeah, so that
Yeah.
m on the left is a negative m?
Yeah, I mean, this is negative m. M is positive, so n gamma minus m is going to be alpha multiplied by m acting on gamma. Okay. In order to prove this relationship, we need, how much time do we have?
It's
just-
kind of a bit late, so I say until 4.
Okay, okay.
Is that right?
Yep. And the idea in order to prove this, the idea for proving these things is proving several technical lemmas and using those technical lemmas to go between the definition of what it means to apply n gamma 1, m1, n gamma 2, m2 to some alpha, subtract this from the other convolution that defines n gamma 2, m2, n gamma 1, m1, and see that the only thing that we are left is a multiple of alpha.
I'm confused. Haven't you said that they commute?
Yeah, they commute when both m's are positive or both m's are negative. However, this delta, so when both of them are positive or negative, this is going to be 0. We can also prove, but it's a little bit more complicated, that if m1 and m2 are positive and negative, but they are not, and their sum is different from 0, and they will also commute, but it's a little bit more complicated than the tools that we have mentioned here.
What's that bracket?
This is the usual pairing that we have on NHO groups of, if we have AX, have the pairing to positive integers, which is intersecting and taking the degree of that intersection. The way we see pairings in convolutions is given by this diagram here. X, gamma 1, gamma 2. I'm taking, there is nothing to take pullback to, so it's gamma 1 intersected with gamma 2 and then push forward towards the product of vertex labels, which is just a point. So this is how we think of pairings, for instance. And we think of several things in using these diagrams. For instance, I have not worked that much with these things here, but a way that we can study intersections with those convolutions is that if we take some x here, or let's say xd, 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 and here we take the class of the diagonal, here we take alpha, here we take beta. This is going to be the intersection of alpha and beta. So we can study these kind of things using convolutions also, but the diagonal of 3 things doesn't behave very well with those operators so far, so I have not gotten any results with just the intersection of those things. I don't know what else to do that will take me less than 10 minutes, so any questions? X is not a surface, those Hilbert schemes may be singular and something like that. And also the fact that those are surfaces allow me to compute the dimensions of the cycles that I care about. And using those dimensions, having those dimensions allows me to prove several equalities here.
All these equalities depend on it.
Yeah, all those equalities depend on X being smooth. I think that these kind of equalities can be used in some other parameter spaces, but I have not worked with them so far. Because this equality is pretty much saying that if I take a union and another union, it's the union of all of them. So these kind of convolutions behave well with parameter spaces. And maybe this can be helpful in other parameter spaces.
So do these negative Nakajima operators they generate the rest of H?
Yeah, they generate, kind of generate. If instead of A we have singular cohomology and we have Kunet formula, we can show that it generates. That's something that I just did recently. So it's a little bit messy how I explained it, but the idea is that for every D, xd, and for every partition of D, I can take this diagram here, a partition sigma of size D, sigma 1, sigma 2, x sigma t, x, those same x sigma 1, xd. For each partition sigma, we have an element in all of those are standard. Everything is standard here. Okay. For each partition d for each partition sigma of d, we get an element of the Chow group of xd times xd. If we analyze its support, its support is contained in all P1, P2, such that P1 and P2 have the same multiplicities at each point of its support. And this scheme here has partition of the components. So we can prove that each of these will be a linear combination of those components. And we can prove that they are linearly independent. Why? Because if we take the convolution with another one of those similar to this one, those compositions will be 0 for different partitions, and they will be a multiple of the same partition, a multiple of the same one for the same partition. So they will be linearly independent. And so some linear combination of these things here will be the diagonal in particular. And taking convolution with the diagonal is an operation. In particular, we'll have that the diagonal, the class of the diagonal, is going to be a sum sigma equal d to some coefficient sigma.
Sorry, I didn't quite understand. Where does this, you said it has partitions of d?
Yeah, for each partition sigma of d, we get some class here. And they live in a space of dimension partitions of d. So, and they are linear independent, so they will, a linear combination will be the class of the diagonal. This will be a rational linear combination, so C sigma is rational. It's not an integer, but almost nice. Okay. If we had Kuhn's formula, for instance, if instead of working with Chow groups, we were working with cohomologies, then this convolution here will be something that lives in the cohomology of x, tensor product cohomology of x, tensor product cohomology of x, tensor product cohomology of x. And the remaining convolution will be taking the products of sigma 1 acting on an element of the cohomology of x times sigma 2 acting on an element of the cohomology of x, and so forth. So any element alpha will be a linear combination of products of M acting on elements of the cohomology of X. And this will give us another way to see why those cohomologies, when we were working with cohomologies, have the dimensions that they have, independent of previous proofs.
So you should think of these the partitions as corresponding. So usually the Heisenberg vertices.
Yeah. These partitions are, I see of them like scramblings of x of a of xd. I have not worked with them so much, but this is something that can be proven with just looking at, with just the tools that we have seen so far. I think we need some extra tool, but it's almost there. But sure.
So the fact that this and the negative ones and both the positive ones that they commute is just the fact that your product itself is commutative.
Yeah, the product itself is commutative, and this is an action of the second argument over the first one, the verb pair.
What I wonder is, so what's your intuition as to whether or not this construction is general or is something that is really dependent on the diversity of points on the surface?
I mean, different parameter spaces will have different properties that we can, different operators that we can attach to them, and those operators will depend on which nice classes we can define on products of those parameter spaces. For Hilbert schemes, we have that nice union and multiplicity schemes. they are especially nice because they are in the middle dimension and explain that convolutions are the middle dimensions, but well, shifted dimensions. But different parameter spaces may have different properties.
I wonder if you can include some non-commutativity by, so instead of like trying to change the product itself,
Mm-hmm.
the spaces where you're intersecting, by changing your class to be not symmetric, your standard classes to be not symmetric.
The A of X?
No, the use that you're using, for example.
Yeah, I mean, it can be done, but for instance, which...
Well, I'm hoping,
Sure.
so I'm hoping to see, for example, if you look at, instead of Hilbert's scheme of points, if you look at principal G bundles, and if
Mm-hmm.
instead of Heisenberg, you can get the affine algebra
Sure.
out of these things. And I can't see how can you see the something like the affine algebra without getting these gamma m's to being non-commutative themselves. And if your product is commutative,
Yeah. I mean, it can be done a little. I mean, as long as there are some equalities with convolutions of standard classes, there can be a structure between with the operators that we define there. I'm not really sure in that case what can we get.
so I guess an associated question, but I think I already asked, but just in case. So if you look at this Heisenberg itself, that you're getting.
If we have Kunet formula, yes.
Yeah, so this is the
In cohomologies, we get Heisenberg.
Yeah, so let's care. I don't care about this.
Yep.
Let's go down to cohomology, have Heisenberg. And now I wonder, it seems to me that you should be able to produce also the modules over Heisenberg or any. Construct the lattice vertex algebra and then see if you get the affine vertex algebra at level 1.
Yeah. Which will be the modular space, the vector space that is the module?
So Heisenberg has for each you're constructing Heisenberg over that lattice.
Yep.
Say, right?
Which is the
So
X.
if you take any character of that lattice, Heisenberg has a module.
Yes.
So I suspect that you should be able to construct such a thing by just playing around with the character. So something that these operators now act instead of on H, on some twisted version of H. So it's a space that is isomorphic to H,
Yes.
now labeled by an extra character of the lattice. So I suspect that the action of H, of your algebra, of n gamma m's on such twisted object should be easy to describe.
Yeah, I think there can be, it's possible to do something.
And then the question would be how to multiply those two such sectors.
Yeah, going from H of X and the other vector space to the vector space itself. Yeah, I mean, as long as there is some class from X, XD, XM, and the other thing, I will have to think a little bit more about that. But yeah, it looks that some representations can be constructed there. I will have to think a little bit more on that.
Already has Nakajima has given more general, using more general kinds of configuration spaces. It's W algebra or something.
Maybe some stuff can be replicated on those contexts. I mean, I may have to force the intuition that Nakajima has on the language of convolutions to be able to replicate this on Cho groups instead of just cohomologies.
So let me ask you this. I'm not so much familiar with the Nakajima work, so correct me if I'm wrong. But all of these operators were considered by Nakajima
In the context of cohomologies,
Sort of,
yes.
Showing that you can consider that in the chapter,
Yes.
which is a finer structure.
Yes.
Can you gain more from that?
There are some things that can be gained from this. For instance, Nakajima's work used some auxiliary cohomology, which is the more cohomology, which is a topological cohomology. So the advantage of this construction is that it doesn't need any extra cohomology. As long as my cohomology has some nice properties, I can stay there. So I can extend this to algebraic cycles. A disadvantage is that, for instance, Nakajima's work is from real cohomology the real cohomology has a super vector space structure. I lose all that super vector space structure in Chow groups because I only have this pairing here. The same properties, but however, the same convolution language can be used there and get something in the notion of, in the context of singular cohomologies, because the convolution is, construction works in general from some category with products and with some fiber products towards some general symmetric monoid. In the sense of cohomologies, it will be taking complex varieties towards super vector spaces. And all the constructions here will apply as long as some technical lemmas are proven. So it can be replicated to the context of cohomologies without needing some extra cohomology to help with that. So that may be help.
But for example, people use Hilbert schemes as moduli spaces,
Yep.
as parameter spaces to do numerical geometry.
Yep.
But to compute numbers, you can just remain in cohomology, right? Or
Yeah. Some stuff, yeah. There are certain things that, knowing that we are working over Chow groups and knowing that we have integer intersections help. For instance, which was something. For instance, these constructions here and some other extra work that I do allow me to compute some cycles in XD. Well, when X is P2, there are some nice cycles that I can be interested in, which is first M acting on the class of P2, which is cycles supported at any point, M acting on the class of a line, which is cycles supported at a point in a line, and M acting on the class of a point, which is scheme supported at that specific point. The language of convolutions allows me to compute these cycles in the nice basis of the source basis. Because certain things are easier to be looked at when we have a graph rather than having a huge mess of intersections and push forwards. So having the language of convolutions allow me to perform certain numerical computations more easily than just. Yeah, it simplifies things.
Your convolutions are well defined on characteristic B.
These convolutions work for algebraically closed fields because I need the closure to define the scheme.
To define the convolution itself and the products itself, you never use characteristics.
Yeah, I never use characteristics here.
Nakajima to construct his construction.
Yeah, he needs an extra cohomology, so he needs some topology there that it's the topology of. Yeah, this can work on any algebraically closed field. So it's, but I only look at algebraic cycles.
That might be picky, but why algebraically closed? You know about to say?
When I define the cycles as closure of locus, I need algebraically closed things. I would like ideally to define those cycles in a more functorial way. For instance, maybe the Chern class of some Chern class of certain tangent bundle, of some vector bundle, or some standard vector bundle, but I have not been able to define it that way so far. But it may be possible to generalize for any field.
Second speaker today, Francesco, talk to us about self-similarity of p-adic analytic pro-p groups.
Good afternoon, everybody. First of all, I would like to thank you, the organizer, Jetro and Raimundo, for inviting me. It has been a long time since I came at IMPA for the last time. It was pre-pandemic, so it is really a pleasure to be here to talk again. Today I will talk about some results in collaboration with Ilir Znopce, who is seated there. So thank you for coming, Ilir. And the subject that I'm talking about is in the intersection between two areas. On the one hand, we have the super classical subject of p-adic analytic property groups. And on the other hand, we have the subject of the self-similar groups, which gained attention in the last 40 years, maybe. And the idea is literally in the intersection. We ask ourselves which p-adic analytic groups are self-similar. And quite surprisingly, it was uncharted territory, and Ilir had the idea to explore this territory, and he had an idea on how to do this. And he shared his ideas with me, and we were quite successful, so I thank Ilir for this. And today I will start by making some definitions, just to put the context, and I will try to give all the results to state at least all the results that we got. I will start on the self-similarity side. For this, I will denote by TD a regular rooted diary tree. What is this? I will write a picture for d equal to 2. It is a kind of graph. It is a tree, so you have a vertex, which is the root. Then this has two children. Each child has two children itself, and so on and so forth. And it is infinite. And we are interested in studying the automorphism group of this graph. So an automorphism is an automorphism of its object as a graph. And this has a remarkable structure. First of all, it is a profinite group. And as a set, the first remark that I make is as a set, it is in bijection with, in general, when you have a ramification index of D, it has this form. This is the set of vertices. So to give an automorphism, you have to, for each vertex, you have to say which permutation of the children you do. So for instance, you can draw a picture which is called the portrait of the automorphism. You can switch these two, and then all this part of the tree goes there, and vice versa. You can keep this part fixed. You can switch this and switch this. For instance, this is a portrait of a part of an automorphism. And in order to convince you that this group has remarkable properties, I will mention the following. In 1902, Bernstein asked the question if a torsion finitely generated group is finite. The answer was proven to be negative by Golod and Shafarevich in the 60s, but the proof was very complicated. Nonetheless, in 1980, Grigorchuk proved that a four-generated group inside this tree, the adic tree, was a counterexample to the Bernstein problem. And the advantage here is that this group is very simple. I could write a portrait of these generators. I will not do that for lack of time, but you can see the construction is very simple. And so this is first of all. And second of all, also Grigorchuk in 1984, he proved that this very group is a group of intermediate growth, answering an open question which was posed by Milnor in the 60s. And if I'm not mistaken, this very group solved another couple of open questions at the time. And it happens that it is a self-similar group, and I will give the definition in a moment. And it is generated by a finite automaton. Here you can think of an element of the tree as a word in an alphabet 0, 1. For instance, if you have this vertex When you go left, it's 0, and when you go right, is 1. So this is the vertex 0, 1. This is 1, 0, and so on. And so an automorphism is going to transform a word in another word, and you can do it with a Turing machine. And that's what this is what's happening here. And it happens that these kind of groups are self-similar. And now I said this just to give more or less the scope of the subject. And to say what self-similar is, I will make this observation. If we have an automorphism of the tree, and if you have a vertex, then you can associate to this data the restriction. How the restriction works, I can draw a picture here. I can take this automorphism as phi. I can take this vertex, and then I observe that this part of the tree is isomorphic to the whole tree. And then I can, the restriction is obvious now conceptually. The restriction of phi to v is just this one. I mean, I take the action downstairs here. So this is phi restricted to v. And then we have a definition. Definition I take to start with a subgroup of the automorphism group. And I say that is a self-similar subgroup if and only if for all elements of the subgroup, for all vertex, I take the restriction. A priori, the restriction is an automorphism, but it can go outside H. And I ask that the restriction belongs to H. And then I'm ready to make the most relevant definition, a very important definition for us. I would like to work with not only with subgroups of this automorphism group. I would like to work with the general groups. So I take let G be a group. First of all, I take an integer, a positive integer, and I say that G is self-similar of index D, if and only if there exists a faithful action. So it is an isomorphism of G with the subgroup of the automorphism group of the tree. In such a way, first of all, H is self-similar as a subgroup, and with this definition. And second, G acts, this is an action by automorphism, acts as transitively on the first level of the tree. On the second part of the definition is that G is self-similar Well, I will make here I will make abbreviation. I will say self-similar of index D. So G is self-similar if and only if, by definition, there exists D such that G is self-similar of index D. The third definition is that the self-similarity index of G is denoted by sigma G, is the smallest on D such that G is self-similar of the things index if D exists. Otherwise, we put sigma G equal to infinity. Okay. Tell me. Yeah, sure. Here you identify. Yeah, you via this isomorphism you can think of an element of G as an automorphism, and then you just ask that for any pair, or here you have the root. For any pair of vertices in the first level, you can find an element of H that sends this to this. Okay. One of the main observations is that in order to study the problem of self-similarity for analytic groups, is that we can define this property, or you have an equivalent characterization of this property in terms of virtual endomorphisms. This was already known. I take a group and an integer, and the point is that G is self-similar of index D if and only if there exists a phi. Maybe phi is not, let's call it phi, not a good notation, from, I'll say D to G, a group of morphisms where D is a subgroup of G of index precisely D, and there is no normal subgroup of G, non-trivial, such that number one, n, is contained in the domain, and second, psi of n is contained in n. I call these two properties to be n is psi invariant. Tell me.
Before you remove the next one, I'm not understanding what this phi restricted to D is.
Yeah, so I will have to redraw the picture. Yeah, this is quite important to get intuition. So suppose that you have, and so on, here, we have, so you understand this picture. This is an automorphism, etc. Then if I take, this is the vertex that I want to restrict to, and this vertex has associated to it a subtree, everything which goes downstairs. But this tree is isomorphic to the whole tree. It is just this is a copy of T2. So you can view this portrait as a portrait of right.
But D is moved by phi, right? In your picture.
Pardon?
The vertex D is moved by phi, right? In your picture.
Yeah, the vertex may be moved, but doesn't matter. Yeah, if you want, it's moved here, but this one is also isomorphic to the whole thing. So it is a kind of conjugation. If you want an isomorphism, formally speaking, you want an automorphism of the original one. So you start from here, you apply the isomorphism that you have from here to here, then you apply phi, and then you go back. It's a conjugation, but of course, if you move this to this, it's a conjugation by two different, but it's a conjugation, yeah, sure.
So it's a group homomorphism?
You have to be careful if the vertex moves, maybe you have some problems, but you have some nice properties that it is well behaved, these restrictions.
So the condition 2 then confuses me a little bit, because I would have expected this condition 2, so the second point of the first condition. So that I take as something to prevent this D. So if you have something that is subsimilar of index D, then you just cannot consider it as subsimilar of index D plus 1 because it wouldn't act transitively.
Yeah, sure. Yeah, that's an interesting point. First of all, if you have, this equivalence works with that definition. At the beginning, when we started to study the subject, this was quite confusing. But it's kind of like you want your action to see the whole tree. So it's natural in some sense to put this condition. Otherwise, well, this is a binary relation between this condition to be self-similar of index d. It is a binary relation between a group and an integer. And they talk, the group and the integer talk to each other, not only via the fact that this is the tree that you are considering, but just as because of you said, you want this condition to the group to see the whole tree in some sense.
So now what confused me is that such a condition there, I would have expected to see in 3 something like the largest d such that.
Here?
Right, so in 3 you have this condition that you define the self-similarity index to be the smallest d that this happens.
Yeah. Well, I can make you an example, an observation. If you have a finite group, it is interesting. It is more interesting than difficult to have. If you have a group, you want to see exactly this one. What is the minimum tree in which it acts? If you have a finite group, for instance, it can be huge, but it is also similar of an index equal the order of the group. But this gives no information. You want to see if the group acts on the smallest possible tree. That's the idea. And usually, if you are able to show that a group is similar of some index, then you are also able to show that for some bigger indices, the same is true. Even if I don't draw any general results that do this, but in the examples, it's like that. So in some sense, it's the smallest thing that you are interested in.
But not for every integer of all d, right?
Not necessarily. Actually, I don't know. I cannot state a theorem in this sense. The example that we have, and sometimes you have maybe the multiples, some multiples of d, let's say. I will make an example later to understand what's the problem.
And then the proposition d is a subgroup.
A subgroup, yeah.
But psi could be trivial.
Psi, yeah, in principle, yes, but I think that if it is trivial, then this condition should not be satisfied because, I don't know if this is general.
Non-trivial, actually. Just put the word non-trivial. You want a non-trivial psi, right?
Yeah, okay.
Otherwise, if you take trivial,
Just do the identity and it's going to be satisfied.
everything will be satisfied. Yeah. Psi is non-trivial.
Yeah, I don't think so, but okay. If you want, I put psi non-trivial, but we can discuss the technical detail later. I think that it is not necessarily non-trivial, but
Simple, that means self-similar?
yeah.
There are no subgroups. G is simple.
Yeah, I don't know. In general, we will see examples. Yeah.
First
Okay.
of all, if you have an action on all these kind of trees, then those groups are residually. So if you act on TD, this is residual with D, right? So you are getting, for example, a Tarski monster can never be subject because it's not residually finite. So you have this kind of action, and actually you will have normal subgroups in these cases because wherever it was, you can get plenty of normal subgroups inside. This is the point. But your point is really good, but the thing is that with simple groups will act on regular rooted trees. This is the thing, such things. So they are contradicting each other. This is the point. Yeah. So in the very beginning, we have residually finite groups. All these groups are residually finite.
We start with residually finite.
Yeah, because since it acts injectively, let's say faithfully on a tree, then you can embed it inside, and then it is residually finite because you can always take these finite images, acting on just a part of the tree. You see why it's residually finite? Because there is also always a vertex for non-trivial element, which will be moved. If it is fixed, everything that it is identical. So if that vertex is on level, let's say 100, then look at the image where you cut on level 101. This thing, that will be finite group, but on level 100 it moves a vertex. So that's why it's residually finite group. Everything there. Every non-trivial element can be seen on a finite image.
Okay, thank you very much. And let me just make a super easy example of this this virtual, this is called the virtual endomorphism of the group, and all these properties called the simple. If this happens, the endomorphism is simple. The virtual endomorphism is called simple. Let me make two very easy examples just to get the flavor. The group now is the integers. You can take the even integers to the integers and divide by 2. This is simple. Instead, if you take the injection, this is not simple. You can take as n, you can take 2z itself.
2z. He wrote like 222. From 2z to z.
But what do you mean simple?
Simple is this. Sorry. Yeah. Simple is if psi satisfies this property, then psi is simple. It's a definition. It's a definition. Sorry. Yeah. Okay. So this one is simple and this other one is not. This is because you have if you can compose, you can take the powers of this, and the domain restricts. If you take the square of this, the domain is 4z, and so on. And it happens that, for instance, a sufficient condition for having simplicity is that the intersection of the powers, of the domain of the powers is trivial, which is the case here. Instead, here it doesn't happen, but this shows that z is self-similar of index 2, and it is self-similar of any positive index by generalizing this example. So we have more or less an idea of what self-similarity is, and now I will change the subject. We all know that if we start with the rationals and we want a complete field, then we either go Archimedean and we get R, or non-Archimedean and we get, for any prime p, the field of p-adic numbers. And we can construct here, so this is our context, we can consider the concept of p-adic analytic group. What it is just a p-adic analytic manifold with a group structure which is in which the operations of composition and inversion are given by convergent power series in convergent the p-adic norm. And in a p-adic manifold, the transition functions are supposed to be analytic, and the point is that the local model is just given by, just as here with Lie groups over the reals or the complex numbers, the local model are open subset of QP to the n, or if you want, inside here in the non-Archimedean case, we have a ring that plays the role of the integers. This is open here, so we can take as local model as well ZP to the n, subset in ZP to the n. If I have a p-adic analytic group, I can associate to it a Lie algebra, as in the case for R or C. Now it is a QP Lie algebra. As a vector space, it's just the tangent space to the identity of the group. And but we need a refinement. So this is just an observation. Need, for our purposes, which I will tell exactly what they are our purposes. And this refinement is given by a theorem by Lazard. (1965), which gives an isomorphism of categories between the saturable p-adic analytic pro P groups and saturable ZP lattices. I will call the map this way. The group associate LG, and the other way around to L I associate the pair L star. I have to define several things here. First of all, what is a ZP lattice? It is a finitely generated free ZP module plus a bracket, so a bilinear operation which is antisymmetric and satisfies the Jacobi identity. So it is a linear algebra, the underlying model of which is finitely generated and free. It is a lattice. Then I have to say what is the definition of saturable. The definition of saturable is given in terms of a map of evaluation from G or L to the positive reals. But I will, with some properties that I will not tell you, I will just want to give you what saturability does, the idea of the meaning underlying. The bracket is on the module, yeah, it's on the module, yes, L. Sorry. Thank you.
It's on the model, okay.
Okay, yeah. And so saturability, we consider with the Hausdorff series equal logarithm x y.
Why are we using word Lie lattice at the same? Oh, so these are Lie lattices.
Lie lattice, sorry. It is a lattice, this is a lattice, and it is Lie because of this. Okay. Now, what's the point?
Say lattice, you never imply. So, yeah, so I guess I'm confused. So lattice does not need to have a bilinear form.
Yeah, I say lattice for a finitely generated free ZP module. Yeah, okay.
And if you L beside the QPs,
Yeah, of course you can tensor L with, yeah, that's super important actually. When you do this operation, what is the relation with this Lie algebra? That's, I have to say first, I just forgot. In which sense this is a refinement of, this map is a refinement of this one, in the sense that LG, you get back your, the Lie algebra over QP as by extension of scalars. But you have this one over ZP only under this, under some additional assumptions. In particular, these one are torsion free. So just you, and how?
Is this something like in the real case, like Chevrolet do the Z form for simple?
Well, I don't know exactly. I mean, I will. This study came out from the successful attempt of answering to the analytic version of the Hilbert's fifth problem, which was if you have a topological group, which condition you have to put on it in order to be analytic, and that's. I will tell exactly just the answer in this case, or maybe I can tell you this answer already, since I plan to do this anyway. Just to put this in historical context, theorem. So the answer to this problem are same here. You take G, a topological group, and then G is p-adic analytic, which means, and P is a prime, and given already, and this means that there is a structure of p-adic analytic manifold over G such that it becomes a p-adic analytic group. If and only if there exists an open subgroup which is with H as saturable, finitely generated, and prop P. So you need, it's this condition that I will talk about a little bit that controls the analyticity of a topological group. A priori it's topological, general, whatever, and you have this, this characterization. So how do I get saturable? I take the out of series, and this is a formal power series with rational coefficients in two non-commuted indeterminates, x and y. Okay, and the point is that I can write it as a formal series of some coefficient which is rational, and I would say u lambda xy, and some terms which are nested commutators of x and y. So what happens here? If I have A and B, two elements on the lattice, I can evaluate each of these terms in A and B because I have a bracket. So these are just brackets of x and y. And then saturability essentially is the weakest condition that I can put in on a general lattice in order this series to be convergent for any A and B and L in L. If you have this convergence, then you define a bilinear operation on this set. You can define a bilinear operation. AB is equal to the series evaluated in A and B. And it happens that with this operation, this is a p-adic analytic group. It's saturable and so on. And you are here. Or it's a p-adic analytic group, pro-P group. Okay. So the first main, so this set the stage. And now I can talk about results. First of all, we can linearize the problem. And this is a proposition of ourselves of 2019. Let G be a saturable p-adic analytic pro-P group suppose that the dimension of G is less or equal than P. This is in fact a restriction, but we cannot do otherwise. I take K a natural number. Then we have that in general, if you have a pro-P group and it is self-similar of some index, the index has to be a power of P. So it is not restrictive to say that G is, if you say that G is self-similar of index P to dk, if and only if some condition happens on the associated Lie lattice. I will take L equal to Lg. And here it is this Lg given by the Lazar's correspondence. And the condition is just a translation of what I erased from here. In the case of Lie lattices, we have a definition. I will write a definition. There exists psi from M to L, where M is a subalgebra. The index of M in L as an additive subgroup is P to dk. So I call it, this is an algebra, an homomorphism of algebras. I call it a virtual endomorphism. And I ask that the endomorphism is simple in the sense that there is no ideal of L, non-trivial, say ideal such that I is inside M and psi I is inside I. So this is the condition of being, let's say, psi invariant. You see that this is the translation of the group statement that I gave before. You just translate subgroup in subalgebra and normal subgroup in ideal, and you get this property. And why this works? Everything works, or this proposition works, because, tell me.
Sorry, you have script L, and then in the theorem by Lazard, you have this capital L.
Yeah. The point is that the coefficients here are p-adic integers. The script L, the coefficients are over QP.
You told us how to associate to G, the script L of G, but what's the L of G, the capital L of G?
This one. No, this one. Yeah, this one is just the inverse of the LG. Is
LG, what's LG?
Yeah, LG is the inverse of this. I constructed here. I constructed given an L. I constructed a group. This is bijective. I can go back. Given a group, I can put a bracket on the same set actually. I can put a bracket as sets. They are the same. LG and G are the same. And because of a result of Gonzalez, Sanchez, and Klopsch, which says that if you have okay, now this is important. I have to state it more carefully. But tell me.
On the left-hand side, this set that you define is just L star, right? Those are L star. No. In the box there, the settable, p-adic, analytic, topi groups are just those that are of the type L star.
Yeah, exactly. Yeah.
Can I take the intuition of thinking of these kind of groups are somewhat of a nilpotent or unipotent group, and that this is just the exponential map in the usual case, or this is sort of like
Okay. No, you can. Yeah, it is the exponential map in a sense that can be explained, but.
Like it's combination of whatever Jeffrey said and you said. Of course, you will have like it can be Chevalier group, it can be nilpotent, or it can be like something involving both of them. Right? This is the point. Everything appears there. In some sense, this should be Lie algebra, but it will get the semi-simple part and it will get the solvable part, and you can go back. I think there's a C-lat that's in Chevalier to algebra, right?
Okay, thanks.
You will state an example later. It's confusing.
Yeah, and so what I will put here on the board, the hypothesis that I will keep for the rest of the talk. So I take here, and then we will make a slight comment. We take G, torsion free, p-adic analytic, rho P group. I take this assumption from now on. And the point is that if the dimension of G is less than P, then it is guaranteed that it is saturable. So if you are, forget for a moment the case where you have an equality here. You have to work a little bit more. Assume it's strictly less. Then this works because, I mean, this translation of subalgebras, subgroup, and so on works because any subset of G, it is a subgroup if and only if it is a subalgebra. It is a normal subgroup if and only if it is an ideal here. So you have this becomes obvious once you see this. But you need this condition. So unfortunately, we have to work only in this under these assumptions. Well, these techniques works under these assumptions. And so I will state a series of results that we got in this case. First of all, we have in dimension, suppose the dimension of G is equal 1 or 2. So in lower dimension, we get that G is self-similar of any index P to the k for all k greater or equal than 1. And this may be done without, actually without this proposition. It can be done directly working with groups. And I will make a comment later if there is time. Tell me.
30 seconds. Right, just to remove and the others, any example there of a Lie algebra and of a property group in dimension 2?
Yeah, sure. Actually, I will make the examples. Oh, I forgot to get examples. Yeah, you are right. I have a page of examples that I forgot to write. Let me see if I have. Yeah, sure. I forgot the examples. Yeah, what are the examples? I have to give some examples also to state the results. Well spotted, Ilir. Examples. So maybe the examples are. I will need the examples later anyway. So the first example is very trivial. Now let me skip the trivial example. So first. So these are examples of this correspondence. So first of all, if I take SL2ZP, this is not even pro P, it's profinite, but it's not pro P. But anyway, it's Lie algebra is SL2QP. And how can we refine this? We can, for instance, take the pro P Silo subgroup. So this can be realized by matrices that are when reduced modulo P are of this type 1, 1, 0, and something. Okay, so a matrix is here, determinant 1, coefficients, periodic numbers, integers, and when reduced modulo P are of this type. And this is an example for P greater than 5, this is saturable but not uniform. I didn't say what is uniform here. We have a refinement here. Okay, let's forget it for the time being. And then we have, for instance, the congruent subgroups here, SLKZP. So the matrices that are the identity after you reduce modulo P to the K, as usual. And these are also saturable, so they have some Lie lattices, and the Lie lattice associated to this is isomorphic to P to the K SL to ZP here. SL2 small letter is trace 0. This is determinant 1. And this is holds for K greater or equal than 1. Okay. So this is an example. I need to write another example for later. I hope to have time to say everything, which is this one. Now I write the presentation, which is nice. Okay, it is another page, but no. Now I start with the lattice. I take D generators. I take D greater or equal than 2, S a natural number. And I take the brackets like this. X0 with xi is equal to P to the S xi, and xi xj, they commutes, and where ij goes from 1 to less than d. And when S is at least 1, this is saturable, and the associated group, I denote the associated group by, this is L ds, and this is a definition. In the associated group, I write it as GDS, and can be seen as a semi-direct product of ZP with ZP to the D minus 1, where 1 acts on here by multiplication by 1 plus P to the S. It doesn't matter. We have here a nice group, the Lie lattice of which is presented like this. And okay, so this makes an example in dimension 2 as well. You take D equal to 2 here. So in low dimension, there is nothing interesting happening. Everything is similar of any index. So let's see what we can do in dimension 3, for instance, where some phenomena start to happen. Okay, always in this, under this assumption here, the dimension of G is equal to 3. I assume for simplicity that the prime is at least 5. And the point is that the group where these groups are classified, the unsolvable ones were classified by Gonzalez, Sanchez, and Klopsch, and the unsolvable ones that were classified by ourselves. And we have, first of all, a theorem that says that, so we have a parameterization of all the classes, and for any values in the parameterization, of the parameter, let's say, the parameters of the classification, we can say if G is self-similar of index P or not. So if we take this as the index P, the smallest P possible, as the most interesting question, we can answer this in dimension 3. And then the behavior that we have is a difference depending on if we take G solvable. Then we have that G is self-similar of index P to the k for any k. And this 2 is just dimension minus 1. This happens here. So everything is similar for solvable ones, and the self-similarity index is either P or P squared. And the behavior is very different if G is unsolvable. If G is unsolvable, we have a fact, a known fact, that G is either isomorphic to an open subgroup of SL2 CELO ZP, or G is isomorphic to another group, SL11 delta. I denote by here. It is constructed out of a central division algebra over QP of dimension 4. It is so a quaternion algebra. So you have it explicitly. For lack of time, I cannot write the definitions. But what is interesting here is that in this first case, we can show that G is self-similar of some index. And we have lower and upper bound for the self-similarity index. Instead, here we have that G, the theorem is that G is not self-similar of index P, and we conjecture that G is not self-similar at all. It's not self-similar. So in this case, we have a dichotomy between these two cases with respect to self-similarity.
So the G in your statement there is G of the form GDS.
No, the G is any three-dimensional, I erased, I shouldn't erase, a three-dimensional torsion-free p-adic analytic property group. We have, if you have this condition, so we have P greater than the dimension, then we are able to classify everything. We know everything here. And for this case, we have these results that I mentioned.
The theorem is used in the classification.
The theorem, this uses the classification. This one, yes, you have the classification, and for any class in the classification, you are able to establish this kind of self-similarity, if it is or not. But for getting this, I can divide in two cases. So this is another result on the same subject, so to speak. And we have a well behavior in some sense, the solvable case, and the unsolvable, we have these two possibilities, so to speak. Now I will.
Is it a property of the ambient group, this dichotomy here, or is it a property of G itself?
yeah, probably it is a property of the ambient group. Maybe there is some theorem that here we have split and non-split. The Lie algebra associated are split and non-split. Maybe you have a big theorem. If you have a split Lie algebra over QP, then it is self-similar of some index. If no split, maybe not. That's will be even a bigger conjecture about. You want to say something? No. Okay, that's perfect. So now I will use these groups for stating some other results. I will make an application in number theory. I will talk about maximal pro P Galois groups. What are they? First, I take a field K, a general field. I take a separable closure of the field, and inside here I take the composite of all the finite P extensions, and I call this composite as KP. I fix a prime, so I have this stuff for any prime, and then I define GKP as the Galois group of this extension, Kp over K. Another way to say this is that this is a maximal pro P quotient of the absolute Galois group of the field. And the point is that is under the assumption that I will write, so in particular under the assumption that this group is p-adic analytic. It may be or maybe not, but in case it is, we can characterize these groups in terms of self-similarity. Let's take here a theorem. So I raise the hypothesis. It's good that I write again. Let G torsion-free, p-adic, analytic, pro P group. Then I assume, okay, G non-trivial, technical assumption in order the statement to work, solvable. We start with statement with solvable, and dimension of G less than P. Okay, then I say that there exists K, a field that contains, here I have a technical condition as well, contains a primitive pth root of 1. In particular, the characteristic is not P, such that G is isomorphic to GKP, or if and only if. So the idea is as follows. If I take K, I get a group here, in general a pro P group. And then, okay, if it is well behaved, it's p-adic analytic, what can I say about this kind of groups in terms of self-similarity is the following, that G and all of, this is a very strong property, all of its closed, non-trivial subgroups are self-similar of index P. So G is self-similar of index C together with all of its closed subgroups, which is a remarkable property, and we call it strongly hereditarily self-similar of index P. Okay, we need this abbreviation later on. And actually here I'm cheating a little bit in the sense that it's kind of misleading propaganda. Now I will tell you the truth. It is true. It is not fake news. It's the theorem is truth. How it's true? How we got there? Tell me.
Slobodan gave us a talk about these maximal Galois property groups in relation to relativity resistance.
Yeah.
Are these two things interconnected?
The p-adic analytic groups
yeah, the point is that these are of the type, here, these groups appear here. I mean, these are either these ones or ZP to the D. That's the point. So we proved that these groups among this class, these groups are the only one that satisfy this property. And on the other hand, a result of where refined by Quadrelli showed that these groups, when are under these conditions of p-adic analytic, are exactly of these forms. So combining the two results, we get this other statement. But our statement is just this one, if and only if this one. And finally, I wanted to talk a bit about the techniques for proving this stuff, but these kind of results of non-self-similarity and so on. But I will just skip something that I intended to talk about, and I will end the talk by speaking about index stability. And the remark is that in order, we want, actually we haven't, we can remove the word solvable here, so to get the classification on a much wider class of groups. And this is still unpublished, but we have already the theorem. And in order to get, and we will have to prove non-self-similarity result for groups of dimension greater than 3. And for this, we need a property which is called index stability. So we need, let's say, we need index stability to prove more results. We need it, no? More results in this context of self-similarity. But the point is that this notion of index stability that now we will define was already studied in other contexts. And what it is, index stability is the following. If you have a group G and let's say two subgroup, we'll call H and K, two open subgroups of a profinite group G. And then G is index stable if, in case H and K are isomorphic. This implies that they have the same index in G. If this happens for all H and K, we say that G is index stable. And the property of this type is needed to get some more result in index stability. But here I mentioned but as I said, it was studied, this notion already in other contexts. For instance, there was a question posed by Reed in, I guess, 2010 question. If you have G, a profinite, or just infinite group which is non-virtually abelian, thus this implies that G is index stable and we got an answer, a positive answer to this question in the subclass of the p-adic analytic groups through the following theorem. We take G, a compact p-adic analytic group. We assume that LG, the associated with the algebra, is semi-simple. Then G is index stable. And the nice thing about this story is that after a couple of weeks after we published this result on the, or pre-published this result on the archive, we get an email from Jean-Pierre Serre just commenting these results, and in In a few lines, it gave the proof of a more general result than this. I will state the theorem here. Theorem. There. Under the same assumption, G is index stable if and only if for all automorphism of the Lie algebra, the p-adic norm of the determinant of the automorphism is equal to 1. So since in case you are semi-simple, the determinant is plus or minus 1, we get this result is a corollary of this one. This result is used, for this we used the Lazare correspondence. Instead, Serge used p-adic integration. This is a compact topological group. So you use R measures and so on to prove these results. And yeah, the point is that this is enough to, now my time is over, so this is enough to, as a corollary, we get, I write the corollary as a final statement, at least the precise statement that we need to answer to the question by read. If I get it, the corollary is that. Let G be a just infinite compact p-adic analytic group, then G is index stable if and only if G is not virtually abelian. If a group is virtually abelian, then for sure it is not index stable, so you have to rule out these groups. And so we have, in this, under this assumption, this extra assumption of analyticity, we have an answer yes to this question. That's all what I wanted to say. Thank you for your attention. Indices are the same, yeah. If you are asking this property, yeah. Yeah, actually, no, let me observe that. Of course, if you have where this doesn't happen, if you go to ZP to the D, so the abelian group, every subgroup here of this, it's finite index is isomorphic to ZP to the D. So you can have any indices with everything is isomorphic to itself. But if you have example in which you have this property, so this is the example that we saw before of SL2, or I think in general SLN ZP. Okay, that's maybe the and I think also these groups constructed out of the central simple central division algebras, maybe delta in general. So that's these are groups that have this property. We can.
You have some groups that are isomorphic, but not through automorphisms of the ambient group, right?
Pardon?
In this case, you have subgroups that are isomorphic, but not through an automorphism of the ambient group.
No, I mean here I mean this property is if you have two groups that are abstractly isomorphic, then they have the same index. Right. And this, so this is true, false here and true here. But no, this is independent, as far as I understand, of an isomorphism, an automorphism of the ambient group. That's.
And you actually have subgroups that are abstract isomorphic, but not through an automorphism of ambient group.
Ah, okay. If you okay, I now understood the question. I now understood the question. Okay.
But this is a very extremely strong property. Actually, yeah, you almost never see in group theory these kind of things. This is the one. Let's say if you have a nilpotent group of class 2, you have a subgroup, and you can always go deep enough as much as you want, and you can find also isomorphic copies, right? So, and this is a phenomenon which happens, but here actually it comes from semi-simplicity, right? From the simplicity of the associated Lie algebra and the non-degeneracy of the bilinear form which we had then, that such a thing will happen. But actually what was surprising, so in this conversation with Seth, he then sent an email. So we started, it was a very pleasant communication with him, like many emails, but he said, okay, what is interesting, he said that he spent quite some time to see are there any nilpotent Lie algebras with such a property, because he needs potency. And actually then after thinking for 2 days, and we realized that actually yes, there are. So you have even nilpotent algebras, of course. The associated Lie algebra will be nilpotent, powerful and simple, but which will satisfy this property of set. Right? So that's why, yeah, but these are really like very exotic examples. He was quite surprised as well. So those algebras are algebras where you look at the derived algebra, it is nilpotent. So the algebra itself is not simple, but the derived algebra, or let's say the automorphism of the Lie algebra is nilpotent, you will have such a property. But it's not a very common. It was something that I always believed it is true. We knew in dimension 3, but experts never. Okay, there is. It might be. So that's why. And actually, luckily, we just took this part and decided to publish because it's a kind of nice characterization, and then we've got this email. Otherwise, if it would be a part of a large paper, it would be lost inside, and no one sees that. Yeah. So it was lucky with Francesco. Let's see, if I work with Slobodan, he will never allow me. It was a huge paper, and many, right, complete as possible. But here, Francesco didn't have any objection. But in 2 weeks, we got this email from Seth, which was interesting.
It's nice to be outdone by Seth.
So, yeah.
Yeah, sure.
Exactly this one.